Hello, my name is Karen Bandeen Roche. I was pleased to greet you in a welcome message, and now I'm very pleased to share a brief extra set of material with you in conjunction with the workshop on biomedical statistics. For the next several minutes, we're going to discuss prediction of binary outcomes with a special focus on receiver operating characteristic curve, or ROC analysis. The two main topics will be just what you see on the slide, as well as one more general important feature of prediction. Here's a motivating example that comes from early in my own career. I was working with a physician who was interested in screening older women for osteoporosis. For a long time at that point, there had been a radiation-based method that was used routinely, dual photon absorptiometry, or DPA, sort of the precursor of DEXA. This physician was interested in ultrasound as an alternative measure of measuring bone density and therefore screening for osteoporosis. And so you can see a description of his pilot data set, which we looked at together. The outcome was osteoporosis. He was studying 32 women from his clinic, age 55 to 77. And in this session, we'll also consider the individual's age, their DPA value, and their ultrasound value. And I will say, just for further reference, that higher ultrasound values indicate a denser bone, therefore a better status. So let's think through how we would develop a prediction and then evaluate how well that prediction works in a situation like this with a binary outcome, having osteoporosis or not. One could consider a single predictor at a time, say ultrasound only, and for ultrasound values, determine a cutoff above which, in this case, one would test negative, higher values are better, negative, and below that cutoff, lower values are worse, declare that the person has tested positive for osteoporosis. And so you can see an example, just arbitrarily, we might establish a cutoff of 1,800 meters per second of ultrasound speed. At or below that value, declare that the individual has tested positive, and above that value, declare that they have tested negative. Now, usually we would be interested in building a prediction rule using more than one predictor variable at a time. And to do this, people typically would use a regression model. As a detail, we would need to use a regression model appropriate for binary outcomes. Logistic regression is such a method, but that's not something that I believe will be covered in this conference. Just consider use a regression model to build a predictor rule. And what such a model would do ultimately would be to produce a predicted probability of the outcome in terms of the predictor variables. So for person I, given that they have a certain age, DPA, and ultrasound value, we could develop what we'll call p hat for a predicted probability. And there, similarly, as for a single predictor, we could declare that the person tests positive if their predicted probability of having, say, osteoporosis is above a threshold, and declare them as testing negative otherwise. So now that we have a prediction rule in hand, we need to judge how accurate that rule is for predicting the actual status of the person. And the feature of accuracy that we are going to consider today is discrimination, whose definition you can see in the slide before you. Discrimination characterizes the reliability with which those with the condition, say with osteoporosis, have worse risk scores than those who don't. So again, for osteoporosis, this would be the reliability with which those who are osteoporotic have lower ultrasound values or higher predicted probabilities compared to those who don't. So going further, we really need to quantitate that general definition, which I've just repeated at the top of this slide. The measures that are the most common for quantitating discrimination in this context are sensitivity and specificity. So you can see definitions for those concepts at the bottom part of this slide. Sensitivity is just the true positive fraction. That is the proportion of those who are truly positive who test positive. Specificity mimics this except for people who are truly negative. For those who truly do not have the condition, what is the proportion who test as not having the condition? And then one more concept that will be convenient to focus on is 1 minus specificity, which is just the false positive fraction. Among those who are truly negative, what are the proportion who falsely test positive? In a word then, discrimination seeks the sensitivity to be considerably higher than the specificity. We want the true positive fraction to be considerably higher than the false positive fraction if we have a good decision rule. So here's our actual example data. And let's consider a predictor that includes age, DPA, and ultrasound. We can create a model that generates predicted probabilities in terms of those variables. And let's arbitrarily declare that the person will test positive. We predict that they are osteoporotic if the predicted probability from their model is greater than 1/2. So based on this, you can see what happens in the table just below. On the rows, you can see the true osteoporotic status, 1 if yes, 0 if no. And as the columns, you can see the predicted status according to our prediction rule. 0 if they test negative, and 1 if they test positive. Sensitivity then, the true positive fraction, is just out of 18 true positives, which you can see here, 17 actually test positive. 17 out of 18 is 0.94. This is an excellent sensitivity. Specificity, similarly, considers those who truly are negative. There are 14 of them. Of them, 11 test negative. So the specificity is 11 divided by 14, or 0.79. This is good specificity. Now, that's all great, but we arbitrarily declared a decision rule. And it might be that we should consider other decision rules. And so that's where the receiver operating curve comes in. The ROC curve is a tool for analyzing predictive discrimination considering more than one cutoff. And in fact, this curve considers every possible predictor cutoff, which basically would be every single observed value of predicted probability. So for every possible predictor cutoff, the ROC curve plots sensitivity on the y-axis versus 1 minus specificity on the x-axis. That is, true positive versus false positive fraction. So if you consider what a good curve would look like, we want true positive to be much higher than false positive, and ideal would be to have a true positive fraction of 1. We truly identify every truly osteoporotic woman, but with a false positive fraction of 0. We don't call any negatives positive. And so that would be a curve that looks essentially like a square. We go straight up to 1 of sensitivity, at 0 false positive, and then sensitivity just remains there. Conversely, worthless discrimination is basically the diagonal looking plot overlying the y equals x line, this would be a decision rule for which the proportion of true positives is equal to the proportion of false positives at every single cutoff. It's just like flipping a coin. So let's make that concept a little more real. This is the ROC curve that actually results in our data for predictions based on age, ultrasound, and DPA. And so once again, a perfectly discriminating rule would achieve 0 false positive fraction at the same time as perfect 100% true positive fraction. And so the curve would just look like a square. What the curve you see before you is quite good. You know, it at least is well above the y equals x line, such that we can achieve a high sensitivity at the same time as we have a quite low false positive fraction. And in fact, our arbitrary decision rule turns out to be right there. I would consider that's just about an ideal value. The worthless discriminating rule is right along the y equals x line, such that at any point the true and false positive fraction at a specific cutoff is the same. The different points you see are all of the different cutoffs that we could have chosen to declare a test positive versus a test negative. We once again want to make that a little bit more quantitatively precise, and so people do that using the area under the ROC curve. And so this quantity has a very convenient interpretation. Imagine in our osteoporotics and in our sample of older women, we randomly choose one woman with osteoporosis, randomly choose another woman who doesn't have osteoporosis, and compare the predicted probability from our test rule between those two women. The area under the curve measures the probability, the proportion of times in such a random selection that the prediction rule would assign a higher probability of osteoporosis to the true case than to the true control. So if you think about what we said on the previous slide about interpreting ROC curves, then strong discrimination corresponds to an area under the curve that approaches 1. That's for the square or rectangular looking curve. Worthless discrimination, where the curve just follows the diagonal, correspondingly has area under the curve of 0.5. And the curve area ranges between those values become increasingly good as the area increases over 0.5 and approaches 1. There's a nice reference listed at the bottom of this slide, very readable, and gives a lot of very useful information having to do with how one can employ ROC curves. So let's go back to the example. Here is our ROC curve once again, just exactly the same one that you saw before. I've added a term here, in sample, meaning that I fit a model to produce the prediction rule, these predicted probabilities of being osteoporotic from age, ultrasound, and DPA. And now I'm evaluating the sensitivity and specificity achieved in exactly that same sample. So for now, just consider the shape of the curve. We're just calculating the area. Imagine shading in all of this area under the curve. Turns out to be 0.88, which is actually quite impressive. So this looks like a well-functioning rule. And I'm just pointing out with that arrow where the area is annotated in this plot, which happens to be a Stata plot. So all of that is great, but that brings us to the one other concept I wanted to make sure you were aware of in this presentation. And so what we've done so far is to consider how well our model predicts in the current sample. But if you think about it, if I build a rule on my sample, it's going to train up and try to do the best it possibly can only on my 32 people. And when I take that rule and try to apply it then to other people, it may include information that was very specific to my 32 and won't perform very well on people who have different characteristics. So what we really want to know is what combination of predictors does best in a new sample when I apply my rule to new people. To employ that decision making, we must do something that is called cross-validating. So one thing to really get out of this presentation, if you're trying to build and evaluate how well a decision rule predicts, you must cross-validate it, which means build your prediction rule, build your model in a test sample, but then you need to evaluate its ability to discriminate in a different sample of people. So we could go ahead and apply that to our ROC curve. Indeed we could in totally different samples. But there's one more concept which is called internal cross-validation, which you can see in the bullets right underneath the first main one. This says for each person I, develop a decision rule based on all the other people. Then apply that rule to the person you excluded, and either they will be a true positive or negative, or a false positive or negative. Keep track of it. For the next person, exclude them, build a model on all the other people, and then evaluate that rule on the model from which they were excluded, and do that for every single person. That's called internal cross-validation, or sometimes jackknifing. Well, it turns out that a macro to do that is not very difficult to write. And so we did that, and it performs a 20% jackknife, which means we do that for every 4/5, build a model, use it to predict the remaining 1/5, and do that for every 5th. And let's apply that to consider two different prediction rules, one that incorporates age, ultrasound, and DPA, and one that only incorporates age and ultrasound and doesn't duplicate the two diagnostic measures, which after all could overlap quite a lot. And so if we cross-validate then, first what I'm showing you is the model for exactly the same predictors whose curve I showed you before, age, ultrasound, and DPA. If you remember, the uncross-validated curve had an area under the curve of 0.88. When we cross-validate, that drops to 0.76. And so indeed, the one that we just built and evaluated in the same sample was quite a bit overly optimistic. Cross-validation was important here. And now, here are curves that compare two models, one with age, ultrasound, and DPA, and a second one with only age and ultrasound. If you compared those two models building and testing in the same sample, it would look like the former model was better. But once you cross-validate on the right, now you can see that actually the model that includes ultrasound but not DPA appears to achieve better discrimination. And so once again, we can see the importance of this is my summary slide showing that a predictor based on ultrasound only achieves a good area under the curve and may offer ultrasound as a good screening measure for osteoporosis. So here now are my couple of additional slides. Just for your future reference, one can achieve inference for ROC analysis I apologize. That happens to be my bird clock. For the sake of time, I am not going to re-record. We'll just listen to that for a minute. And then at the bottom, there are further useful measures that exist that we have not covered. The Breyer score is one of them. Net reclassification improvement is yet another. And I've listed a reference at the bottom of the page for those of you who are interested in more. And so the two main points are that we talked about discrimination in considering the quality of prediction rules for binary outcomes based on sets of predictors. We described discrimination as the reliability with which cases or true positives have higher predicted probability than non-cases or true negatives. We discussed specific measures of discrimination, including sensitivity, specificity, receiver operating curves, and areas under receiver operating curves. And then the second important concept we covered was cross-validation, in which, in any context, which one is building prediction rules using predictor variables and then evaluating how well they work, we must cross-validate, which is to say to build the rule in one sample and test its value in another sample. That concludes my presentation. Thank you very much, and I hope that this has been helpful to you.